In this episode, let's look at parameter estimation, and in particular some interesting special cases. So we have a parameter x that we're interested in. So we have the probability of x, and we acquire some data. And what we want to know is what is the probability of x given this data. So again, we apply the usual Bayes rule, so that the probability of x given the data is going to be given by prior probability of x times the likelihood divided by the evidence. Now let's assume that we're only interested in the most probable value of x, and we don't care about the rest of the distribution. Let's also assume that the prior probability is constant. Since the evidence is independent of x, and now the prior is also independent of x, we can remove both, and we'll have that the posterior distribution is going to be proportional to the likelihood. Those other factors which were independent of x are just going to multiply the distribution, and they're going to just shift it up and down. But we don't care, because all we're after is the most probable value of x, and shifting it up and down is not going to change that. So now we can say that the maximum of the posterior distribution over x is going to be the same as the maximum of the likelihood over x. So our best estimate of x is going to be obtained by the maximum likelihood procedure. So we've just discovered one of the traditional procedures for inference hidden away inside the Bayes rule. Let's go further. So let's assume that the data we obtained is in fact n pieces of data. So the proposition that we obtained data D is in fact the proposition that we obtained data 1 and data 2 and data 3 and so on to data n. Furthermore, we'll assume that the data are independent of each other. So then the probability of data 1 and data 2, etc. to data n given x is just going to be the product of each of these pieces of data given x. Let's label that as our third assumption and put it aside. Now in addition, let's assume that the noise in x is Gaussian. Let's say that if we didn't have any noise, then at the parameter value x, the jth data should yield the value f sub j of x. Then, since the noise is Gaussian, all deviations from this true value are given by a Gaussian distribution. And so in particular, it'll be the exponential of minus the true value minus the data all squared divided by 2 times the variance. This assumption that the only noise in the problem is independent Gaussian noise is going to be our fourth assumption. Let's add it to the list. So now what does this mean? Well, the probability of all our data, data 1 through to data n given x, is going to be proportional to the product of n Gaussians, one for each of these data points. And we can ignore any factors that don't depend on x because we're only interested in the most probable value of x. We can simplify this further by realizing that the product of a whole lot of exponential factors is just going to be the exponential of the sum of those factors. Finally, remember we're trying to find the value of x which maximizes the likelihood. But we could equally well find the value of x which maximizes the logarithm of the likelihood, since they are monotonic functions of each other. Now we've been ignoring the factors in front of the exponential. After we take the logarithm, this will become a sum where the first term is going to be a constant, still independent of x, and we'll continue to ignore it. And then the logarithm is going to undo the exponential and just leave behind the sum that was in the exponent. Now, since we're maximizing over x of a negative quantity, this will be the same as minimizing over x of the positive quantity. And since we're just after the value of x which minimizes this, we can ignore any overall factors such as the factor of a half. As you've probably already recognized, we've arrived at the weighted least squares procedure. If the variance was the same for each data set, we'd also be able to ignore that factor and would have just least squares. So again, we've arrived at an orthodox estimation procedure buried inside Bayes' rule. Now, before you decide to throw away the whole Bayesian inference and stick to the maximum likelihood and least squares, remember that we only got here when we invoked a whole heap of assumptions. If any of these assumptions break, then least squares or maximum likelihood may not be the correct thing to do. On the positive side, we've now got a procedure for being able to find out what is the correct thing to do. So perhaps the noise is not Gaussian. You could then put in a different model. Or perhaps the data are not independent of each other, they're correlated. Again, you can work that into the inference process. Or perhaps you have prior information that lets you know the parameter range over X. And finally, the posterior distribution is a rich object that's telling us a lot about our inference. The most probable value of X is only a single piece of that information. We should make the most of all of it.